Does it make sense to explain how mammals should have behaved during the Jurassic or Triassic period, or any period before they existed? Maybe there was mammals then, that like tiny rodents or something. I don't know exactly, but I'm talking about like, I don't know, woolly mammoth or like a panda bear, right? Um, why then do we assume theories of our universe's origin uh, like it has always worked the way it does now? We are using the fundamental forces of particles to describe and conclude behavior of particles, but this is like explaining the behavior of a dinosaur off the behavior of a mammal. Um, just because this is how animals act now, this is the animals we have now, it does not mean that that's how animals necessarily behaved back then. It doesn't mean that they're a one-to-one comparison, right? We can't observe them necessarily, but we have some evidence to show that maybe they didn't act exactly the same, right? And why do we assume that the fundamental laws of reality have always been functioning the way they are? I've talked about this in that basically I think particle physics has evolved over time. We didn't start out with quarks and protons and electrons working the way they do. That has slowly developed over time. And so when we look back towards the start of our universe, right, the Big Bang, it starts to get harder and harder to predict things, and things start to get fuzzy and weird, and things fall apart because we're trying to use mammals to describe dinosaurs. It doesn't work because they're not the same thing. And I think I've already talked about this, but a flaw that I see everyone mentioning often is how fast the Big Bang happened. Oh, it was barely even seconds. Like, it happened all so crazy quick. I don't think that's right to assume that. I think that it's more logical to assume that because everything was more compact, gravity was higher, time moved at a relative to that time frame, time moved normal, right? So what was not even a few seconds looking back now was trillions, billions of years, I don't know. But it was a substantially longer process than we assume it to be. And I think that that's very important. I think that that's an oversight. And I feel like some laws, like we have like relativity and stuff, they just kind of gets ignored in places, and I don't really understand why. Like the implications of relativity is insane. And I feel like we kind of ignore it a little bit because maybe it's a little scary what it implies. I don't know. But so the cosmic microwave background radiation is not necessarily from the Big Bang, but my opinion is I don't think that all of the cosmic background radiation is coming from the time of the Big Bang. I think it is something that has accrued over the development of the Big Bang. So it's not like literally everything in the universe has come from the Big Bang, right? So during this time, I think this cosmic microwave background radiation has been building and is the result of just everything in the universe kind of spewing out energy haphazardly. And we're getting this kind of haze or fog, basically. And so the cosmic microwave background radiation is not necessarily from the Big Bang, but accumulated from a low energy radiation from mass over all of time. This radiation is dark or invisible to us because the energy is too low, but when looking far enough, it becomes known like a haze or light fog. This is why there are cold spots where there are voids. In my opinion, that doesn't make sense. It should be hotspots where if we're just looking at the background radiation, the hotter spots should be where there's less mass, because where there's less mass, there should be less energy absorbed. We shouldn't see hotter spots where there is mass. And I feel like that's an argument to my case, that mass is what is releasing this microwave background radiation over time. And it's pretty even everywhere because it's scattering out evenly, in every direction. So even in the cold spots, this is visible, but it's also not necessarily coming from those cold spots. It's just kind of scattered all about. And the argument is that, well, in these voids, the energy is stretched out more. And so because there's less gravity, it gets stretched out more, and then it starts to lose energy. So it's a little bit colder. And I have opinions on things getting stretched out in in voids. And I don't believe in wavelengths. So there's that. But I think that I don't think that that's necessarily a good explanation for it, because we know that gravity impacts light, right? And so if gravity is impacting light, then areas with higher gravity should be affecting the light more, right? Because we know that light gets I guess that's my assumption. Actually, I can't say that yet. But I think that this is basically coming from I think that even energy is not conserved in our universe, right? And I think that even in photons, because I believe photons are massive particles, massive as in they have mass, not as in very large, but they are radiating energy, right? But that energy is too low, because photons is the smallest we can see, right? So anything that a photon's radiating isn't enough energy for us to see. And so it appears dark, but when all of it gets compiled together, it is added to this very cold microwave background radiation. And I said light doesn't stretch with the expansion of space. I think that the tired light theory, I found out was a thing. I thought that was just assumed that's what was going on. I thought we thought that photons were losing energy over time. I didn't realize we just thought they stretched out, and so that's what gave them a longer wavelength. I disagree with that opinion. But the tired wavelength theory makes more sense to me, that energy is basically lost over time, and like this energy that the photons are losing as they fly through space is this low energy radiation that I'm talking about, right? And over time, this has filled up all of space, but it's very low energy, so it appears quite cold, and so fluctuations seem within reason to call it all, about equal, but it's not. And I know that the difference between these areas is very, very low. There's not much difference, but there is a difference, and that difference is important because that means that we have higher concentrations of fog where there is mass, and lower concentrations of fog where there isn't mass. And to me, that points towards sources and voids, right? So to me, it seems logical to assume that the source of this radiation is actually from just any any point of mass, including photons. But again, that's why it's so equal, because photons get shot out in every direction, everywhere, right, by all of these things. And so as these photons are traveling literally everywhere through space in every direction, they are releasing this energy, creating this haze. And we don't need, and so we can look at it and assume kind of how the universe has evolved. We can still use it like that. It's just, we didn't need it to be this high energy, slowly stretched out as it traveled all through space kind of thing. The entire universe has been slowly expanding out. We don't need all of the energy to be coming from the very beginning for it to be still all from the very beginning. If what I'm saying is making sense, right? We don't need what's left over around us to show just how hot it used to be. We can kind of infer what the universe used to be, what the universe used to be like, by just kind of looking at how the universe is now and looking on how it's expanding, and things and such. And I don't think that I don't think that I'm necessarily disproving all theories about the cosmic microwave background radiation, but I also think that we have it a little wrong. So this gets to the point of, look, I mean, I don't have a good concept of this, but from the photos that I've seen of the cosmic microwave background, or just our universe, we look at it and people say our universe is flat. And I just did a talk about why the Earth looks flat. And I think that we can use similar logic and put it on our universe. I don't think our universe is flat. I think our universe is pretty much globe-shaped, except when we look out, we are getting, I don't know if it's necessarily gravity that's the factor here. This is where things start to get more skeptic for me. I don't really have any solid backing on this. I was just kind of writing this out and this came to me and I was like, that sounds good. So I'm going to say it here, but our universe's gravity works more like time. Anything in the past is beyond our realm of influence, like how we cannot dig all the way to the Earth's core. We cannot fly to the center of the universe. We cannot fly to the center of the universe because the universe expands out equally, and so it is like trying to stop or reverse your motion while in a bus or train. You can go backward, but you will always be moving forward while you do it. As such, whatever is within our time is visible and appears to us as plane-like. But this is merely perspective and time dilation at play. And so what I'm saying here is that we look out and everything looks flat and you can almost see a horizon. We almost have like a horizon forming, right? And then we have some stuff that's up here and some stuff that's down there. And some of this stuff is like, our universe is flat, but it's also a three-dimensional flat because we're heading into a whole nother world of what the heck, right? And so we look at time as this plus one dimension because time is kind of bleeding through into our reality, but it's from a higher dimension, basically. And so we have our 3D universe, right? And so gravity is kind of this deciding factor of how certain things work, right? And so we have gravity, and then then we go up a level, right? And then we're in the universe on this 3D plane where we can go like up and down a little bit, but we can never go all the way down, right? Like on the Earth's crust, you can go up and down a little bit, but you can never go all the way down because the pressure and gravity starts to get too strong. And it's the same thing, but with time for our universe as a whole. And so we are on a globe, but instead of it being a flat 2D plane globe, we are on a 3D plane globe. And time is flowing into the universe the way gravity does, into the center of the universe the way gravity does, right? And we are appearing to expand out through time, right? The way that gravity, like the way that things can get thrown out through gravity but seem to fall back down. It's a similar thing with us for time, except we're basically stationary compared to time. So time is just flowing past us, just the same way that gravity is always flowing past us, but it is, we don't necessarily feel it. And I don't necessarily have hold on. Actually, I have more. The line we appear to see is the horizon of our view. That does not mean we cannot see anything beyond it. It just means that those objects that we can see beyond it are significantly redshifted to become visible to us as the light is bent around our universe. And this goes to what I was talking about. When you look at light that we want to see over the horizon has to kind of shoot up and bend towards us. And since there's really we're looking out, and so it's kind of hard to tell what is like kind of where. I guess you really just have to base off of redshift, because things can kind of be everywhere. But some of this stuff is beyond the quota, is like kind of heading beyond the horizon basically, but it is bending towards us, and so we see a red shift in this. The line we appear to see is the horizon, right? And it's been around our universe. And so I'm basing this off of, I went on a flight and I took a photo of just basically a plane of clouds, just like it looks like a flat plane of clouds, and I'll put all the photos up and put them in a line to show the progression here. And basically I took a photo and I thought, I wonder what would happen if I, took this photo and I increased the saturation and the brightness and these colors and stuff. And if I tried my best to enhance the colors that are present here, what would emerge? And so I took my first photo, right? And I'll put them all up. And then I kind of did this, the changes, and I got this white, light blue, darker blue, and then an indigo kind of layers. And I was like, okay, well, that was a promising first start, right? Now we actually are seeing this gradient. And this is really interesting because it's basically what I've done is I've approximated all the light that's approaching me, and I'm already seeing a shift in the wavelength from white to different bands of light here. So then I continued this process and I did it again, and I started seeing a little bit of green and a faint red band kind of get in there. And I was like, okay. So then I did it again, and then I got a defined green and a defined yellow and I got that red one there, and I was like, okay, there it is, the red. And then I did it one more time just to make it absolutely apparent, right? And so I get this bright green, this darker blue, this kind of indigo. I have an orange line in here, then a bright red band going across, and then below that is basically like a whitish, slightly red, and that's as far as I took it, because I felt like at that point I wasn't really going to get much more, and I felt like I didn't need to do a whole lot more to kind of prove what I wanted to say. But what really shocked me when I went back and I looked at this, after doing this, I went back up to the beginning image and I looked at it, and if you look at them side by side, I expected to see the red band right on the horizon. That's where I thought it would be. Because to me, the red should be right at the bottom, and then we just slowly work our way up. We'll have the bands of higher wavelengths because those are the ones that are getting bent less, shifted less, right? And so that they'll be higher up. And so when I compared them, I realized that there's actually a significant gap between where I thought the horizon was and where the red bands actually start. And this intrigued me a little bit because, I didn't expect it. But at the same time, it does kind of make sense that there's a certain point where the redshift hasn't quite reached yet. So we have our horizon, right? Everything in front of us going out to the horizon is normal, right? It appears relatively normal to us. And then anything that's slightly above the horizon even should appear normal to us. But as things start to get farther and farther away, those things are going to start to look redshifted. And I'm kind of intrigued by these results and what they could mean, right? Because I feel like this also could imply that if something appears blue shifted, it's not necessarily that it's coming towards us, it's that it's even farther away than something that's been red shifted. And that would just be really interesting. And also like a big, I don't know, like, because we're looking out so far into the universe at this point that our only way of judging how far away something is basing it off of its redshift, right? But what if we're wrong about assuming that redshift is the farthest? Redshift's the closer stuff. Things that are blue shifted, now that is far. That would be really interesting. I don't know how we could possibly prove it because we're looking so far away. There's really no way for us to get an accurate measurement of distances at this point. We're basing it all off of the shifting in wavelengths. Yeah. So I kind of looked at this result and I'm like, interesting. Also, I want to kind of say this just as a random tangent here. I feel like I've always been told that the reason why our sky is the way it is like the color it is someone says it's because of the oceans. I feel like I've heard that pretty often. And I think it's either like, I don't know if the explanation of, well, that's just the light that scatters the best or something like that. It's because of the ozone, the way the light scatters off of ozone or something like that. It just causes it to be blue, something along those lines. I don't think it has anything to do with that. I think it's just the fact that the light that is blue shifted is the light that travels the most like up, right? And like it overpowers any other color in the sky at those heights. And so that's why like it looks blue because all of the blue bent light is flying over higher up. So when we look up, all of that light is that's all blue shifted. And then if you go higher up and you get like into the high atmosphere, it'll probably start to look more indigo, because that's where all of the or violet, because maybe probably more indigo, because that's more of a blend of blue and purple, and you probably wouldn't see just straight indigo, but violet. But yeah, and so as you go up, it would probably start to look more indigo and like a darker blue, right? And then at sunset, the sky starts to turn this pinkish red, and we get these oranges in here. And that's because when the sun's setting off in the distance, the light that's traveling towards us is no longer primarily the blue light that's flying over. It's all of those red and orange shifted lights, because of how far the sun away is from it's no longer directly over top of us. Now the light that's coming from the sun is getting shifted into those where the shifts are landing on the planet is also happens to align with when it sets, which it does make sense. I don't know. I feel like I'm rambling here. Basically what I'm saying is that the sky is blue because of the way that gravity bends light, and probably also the size of our planet. But we're going to move on from that now. Anything beyond the redshift region doesn't reach our eyes. I'm questioning that. I'm not so certain anymore. This is also why the sky is blue. I just talked about that. The same principle applies to our universe. This is why we see time as a +1 dimension. It is the flow of gravity in the perspective of a ball whose surface is 3D rather than 2D, than a 2D plane. This gets beyond our comprehension, but explains why there is no back in time. There is only the constant moment in which you are falling. You can't go back in gravity, just like you can't go back in a river. The river you move back through is not the same river it was when it passed you, just as the gravity isn't the same gravity that passed you. Now, you can technically go back in gravity if you're falling and you start falling, you have rocket boots on or something, and you start falling faster than you would fall than terminal velocity. Once you're falling faster than terminal velocity, you're going faster than gravity. But basically that exact analogy is what it takes to go back in time. There is no going back in time, because in order to go back in time, you need to go faster than time, which sounds counterintuitive. You'd think that doesn't really make sense, but it does make sense when you think about the speed of causality. We know that once you start going faster than the speed of light, we know that the speed of causality, when you go faster than it, then you can see effects before the cause, and that is you're basically going back in time at that point, right? Because you're causing something before you're causing something to happen before it happens, right? And so when you go faster than the speed of causality, you're actually kind of going back in time. And so that's why we can see ourselves going forward in time. Yeah, we can do that. Because pretty much what we need to do for us to go forward in time is just just go. I mean, you're not really necessarily going forward in time. You're just slowing down your time. Because imagine um, like time passing for you is how fast, a current is flowing past you, right? And so if you are swimming upstream, right, at, we'll say it's flowing at 5 miles per hour and you're swimming upstream at 2 miles per hour, right? The bank that flies past you on the outside, like the riverbank on the outside of this river you're swimming in, that is how you're judging time, right? As you slowly move down the bank, the riverbank, right, that is time passing you. And so if you're swimming at 2 miles per hour, but you've got a buddy that's chilling at 1 mile per hour, they are going to experience time faster, right? They're going to move downstream faster than you are. But, you know, are you really traveling forward in time? It's more like you're just kind of slowing down the flow of time for yourself. So is it really time travel? I mean, yes, but it's like a relative time travel. But in order for you to go back in time, you need to go faster than 5 miles per hour, right? You need to be swimming at, really you just need to swim at just a little bit over 5 miles per hour. But the energy, it sounds like, oh, easy, I can swim faster than 5 miles per hour. Maybe you can, but that's not really the point I'm trying to make. I'm just using random numbers. But you would have to be swimming faster than 5 miles per hour to go back in time, right? And then all of a sudden you're swimming upstream again and you're going back in time. But in order to do that in our universe, we think it would take basically infinite energy because time time is pretty fast. Yeah, time's pretty fast. So we don't really we don't think it can be done, but that if it could be done, that's how you would do it. You would have to go faster than the speed of causality in order to go back in time, which again makes sense. But again, are you really going back in time so much as just causing things before the cause? I'm not sure. It really gets a little funky. I don't think our universe is flat. I think it looks flat, but I think it looks flat for the same reason the Earth looks flat from standing on it. But if you were outside of it, obviously it doesn't look so flat anymore. And I think we would notice the same thing with our universe if we were capable of doing that. I think that our universe is not flat in the same sense as a sheet of paper, but is more like a stack of paper. The stack of paper is still flat, but it's a stack of paper. And so I think that is a better kind of image, but then that stack of paper is actually a ball. And so we're expanding out through time, and so we're heading out in all directions. And so things that are farther away seem to be moving away faster because they're moving, like the angle between us moving directly out is larger. If I said that correctly. Yeah, I think time is kind of bleeding through from a higher level, yeah, I don't know. I don't know what I think I said everything. I think it's pretty clear. I think it has some pretty crazy implications, and also not all that much. But I do think it's important to kind of think. I realized that the start of this was talking about background radiation. So I guess this really kind of went all over the place, didn't it? But yeah, I think there's a lot we still don't know, and I think a lot of people don't realize how little we understand. So yeah, peace out.